you just connect with the HDI, Human Development Index, with the energy. So they are very much associated. And even this is a very established fact. The country or maybe the person who use much energy, they consider to be more developed. Okay, I'm using the word consider to because it may also depend. So, but technically it is a well acceptable fact. And if you see here the plot, so see that the bottom it is giving as the per capita primary power consumptions in the multiplied by 1,000. So you see these countries, Zambia, Afghanistan, Niger, these are see using a very less energy and corresponding. If you see their human development index is also very very low. Even we are also somewhere here. The India is somewhere here, but you see other developed countries. Then even some other countries, USA, Norway, UAE, but they are having more, I would say, extreme climate. So therefore, they are using much energy. But we would be happy if we can lie somewhere here. And when we talk about the Human Development Index, you can consider we look about the health, education, and the living standard. So if you summarize and see the recent literature, we can say that India is using roughly 1395 kilowatt per energy in 2024. Is per capita, like per person, it's average out for everyone, and which is still the one third of the global energy. Like that means we are still very less. See, okay, I'm not uh, saying that or encouraging we should utilize more energy, but do we capable to utilize the energy? That is the question, right? So if you have money in your pocket, you are not doing any expense, it's okay because maybe not required. But if you don't, then there's a concern, right? Or do you think about future? Can we look out this scenario? So to fulfill our energy requirement and improve human development index, we need to think of, and also if you look about the India aims, so India is aiming can develop a electrochemical setup. We can have two different chambers, okay, and which is connected together between we do oxidation inside and reduction in the another side. Like this way we can set out the hydrogen and oxygen. You can see here. Suppose we are having one type material because you need to harvest the solar energy. This reaction based on the solar energy. We want to utilize the solar energy. We also can utilize electricity. So we have more aspects. If material is not sufficiently working only the solar energy, then some of the electricity. But look forward, the experiment spontaneous on the system process. So if you see here, this if we enter here, then oxygen take place electrode. We call it the working electrode, and oxygen counted be basically going to convert H1 to H2 and going to produce the hydrogen. So that can we use two chamber make the setup put the of the solar or the simulator. Since we do labs, we use the solar simulator. But the issue is that we have to evaluate the performance. Okay, we need to test the performance of the our materials. We need to compare. So we do in a lab, and we also integrate with one setup with the potential state, so that we can apply some current, and with respect to that current we can see what are the changes there or how our setup work, and based on that we can also calculate the conversion efficiency, how much photon is getting converted to the electricity. So we generally use this set. I think detail you can see teacher if state. So ultimately, the thing up toward the material, we require material which can have appropriate properties, can to drive this reaction. So again, different properties, but there are some which we are listing here. The BEP is important if you are looking about the spontaneous reactions, because you minimum energy is required to drive this to break down. It's almost 1.23 electron volt, but this theoretically, but in ideal conditions it is okay. In real conditions we need to supply some more. So we require the band even greater than 1.2 volt. As I said, the reacts depending upon the how we are harvesting the solar energy. So we have to look out the absorption capacity. So we had a material, other conductor material which has very photo absorption capacity, almost order of 10 to the power of 5% universe. Similarly, once generated the electron and hole, these electron holes are basically driving this reaction. So should have sufficient energy, and they also move faster. If they are not moving faster, then of course your overall performance is reduced. So we need to good electron mobility, roughly you can say in this order. Similarly, they should be stable in electrolyte, major challenge. Are putting a conductor material with an electrolyte, and also illuminating with the light, so it may have the oxidation. Suppose you are driving an reactions, so not be happy your material or electrode is getting degraded, getting oxidized. Okay, that's a common possibility. So it should be stable on that conditions. So of course, we need a good catalytic sites. The material should be crystalline. So these are more technical aspects, but these are two are the aspects which need to look out. One is the material should be earth abundant, otherwise can't go for the higher scale. And because to look about the cost, the processing also, and it is high possibility to scale up or the high yield. So whatever material we are or whatever process we are adopting, can it be scalable? Can we make it to the higher scale? So that are the concept we look at when we design a new material. So now I will just sum our work. So we adopted earlier one material which is very popular. I think most of you know about this material work also. So zinc oxide impacted. Why? Because we just covered the parameters, whatever I just discussed. And material has at least few properties which is relevant to your application. And we have used, so we use material, these kind of, these are related around the substrate. When you love the electrode, if you are making no part in the electrode, then another the stability and the unity is one issue. So we thought of why not just we grow the structure on the substrate and as a electrode. So we use zinc oxide system as uh, what we have done. So we adopt several strategies. What was the issue? The materials wide band gap, only able to harvest some of the light of the solar, because you know the solar energy lie in almost 5% UV, around 50%, less than 50% in visible, then Ni. And this material is only sensitive for UV light. So it is having when you are not able to harvest the light, how you utilize. So the one challenge. So of having some kind of change modification. So we adopt first strategy we adopted. We modify surface with the sulfide. We develop the zinc oxide, zinc sulfide core cell structure, and see here the is we just confirm by the ST analysis, and surface just converted into zinc sulfide. The core is the zinc oxide, and the core cell structure is helping us in many various way. One is it is basically reduce the band gap. It also help us to separate the carriers, and it is also gives us better stability. So again, we tested these properties, but thing was okay. Then with other material, we modified this zinc oxide with size control gold nanoparticle. I think you can see the images here. So these different size gold nanoparticles are coated there, and we just adopted a simple strategy. We just coated 50 in the size of the gold nanoparticle, and it has a very good impact over the photoelectrochemical performance. We tested, I'm not discussing all the detailed data, but what we observed, after doing all these modification, we only achieve roughly 1 milliampere per centimeter square current, which is still very less. If you look forward about the industrial understanding or the requirement, it should be roughly more than 10 milliampere per centimeter square if you would like to think about the industrial application. So it's still very, very less. And of course, the stability was another issue, though it's a metal oxide system, but it's still not very stable. After a couple of hours, it get degraded. So we have done all these analysis. So we also thought of another material. So TiO2 is also very popular. We developed the similar structure using the TiO2. As you can see here, the top view and the cross-sectional view of the TiO2 nanorod. We also doped with the TiO2 surface with the nickel. And then we again, as I used in earlier study, we coated with the gold, palladium, and we developed these structures in another study. I think you can see here just some of the how this absorption profile is getting changed when we modified with gold, palladium together. And as I said, it's a wide band gap material, but it switched toward the visual light active material when we modified these metallic systems, this coating. Also, we utilize narrow band gap material like copper, iron, tin, sulfur based systems, and we develop the structures. It may look like something this the coated at the top. Then we have just performed the elemental analysis, and then we in all the systems we tested their performance. And here, whatever the best we received, it was the nickel dope TiO2 nanorod and coated with the copper iron tin sulfur systems. So we reach almost 3 milliampere per centimeter square. That was the power conversion efficiency. So see, the same time we were also thinking that I think anyway, might be. Anyway, don't panic. I think there's no issue. We can manage it still. So I think it's good to have a break. We can laugh 1 minute and then we can start our discussion. Don't worry. So see, we worked earlier in the two different set of materials. One was the zinc oxide, second was the tin oxide. Then we thought of why not look forward the P-type material and which having with a lower band gap, and we started with the copper oxide system. And then again we utilize a sputtering based setup, with a solution process also. We developed the different type of nanostructures on the surface of copper oxide, basically the uh, FTO and with silicon also. So again, here we published this work on these different journals. So what was the strategy we adopted? We surface treated copper nanostructures. We did rapid heat treatment also. Even we just developed some oxygen rich compositions, and we again modified with the copper palladium mix. Even we also tailored the morphology, as you can see here, the different morphologies. And in these systems also, though it's a P-type material and having a very low band gap, but still we could not achieve the performance is very high. It's again 1 milliampere per centimeter square. So after thinking on this, we just summarize what we are still doing. So what was the generic philosophy or the idea? You also look out the literature, you will see the people are doing the same. Either we are adopting the doping of the material, so we can improve the conductivity, we can tailor the band gap, but it is creating some kind of defects also, which are reducing the performance. Surface modification, as I shown, it is also one of the topic which has been explored a lot, and everybody try to develop different strategies. It is helping us, but it's still not so good. Nano structuring is another aspect which is helping us in the way of high surface energy or maybe surface area, interactive sites, enhancing the charge transfer kinetics, quantum size effect. But they are good, they are helping us, but not that much what is our expectation or at least the requirement. So further, now we are thinking about develop the nano heterojunctions so that we can tune the energy band gap. The requirement is that we are still stuck with the UV segment and some part of the visible light. But I said more than 50% lie in the NIR segment. So can we also target to harvest some of the NIR segment, and then it may improve the overall performance. So last almost 4 5 years we are working on this direction, and this was our philosophy. Can we develop some structure which has the 3 layer kind of systems? So one layer can at least take the UV light, another system can harvest the visible, and the last system can harvest the NIR segment. How we can do that? So we can use again zinc oxide or tin oxide based system, or maybe the binary metallic oxide based systems. And as I seen earlier in our case, and then we utilize some NIR light active nanomaterial as a heterojunction. It could be carbon or carbon graphene quantum dots, or maybe the copper oxide quantum dots. So we are working on these directions. So what was our basic material as you see here? So we have divided into the two part. This is the one, the base material, and then this is the material which we are going to adopt as a heterostructure. So we started working with the zinc tin oxide. Why the zinc tin oxide? Because as you see, we put the emphasis on this, the electron mobility, the electrical conductivity, chemical thermal stability. So this is relative, having some properties better than the zinc or tin, or maybe the TiO2. And so how we started? So earlier we developed some kind of nano rod directly on the substrate, but it seems slightly at the very beginning difficult to grow the structure. So we started with the preparing the nanoparticles, and we developed the nano cube of zinc tin oxide. And then what was our first impression? Let look out there, surface profile. And if we do the change on the surface, what is going to happen with their photoelectrochemical performance or the photosensitivity, because which is the one tool which help us guide us to decide whether the material is good for this application or not. So here we just perform simply heat treatment. So we heated this material at various temperature. You can see here, I think not visible at the back, but this bottom one is ice synthesized, this bottom profile, this one. And if you see 152, we have heated at 850 in normal air. What happened? You can see the profile change. That means there is a very uh, distinguished structural changes are there. Okay. And we said that it basically transform from crystalline phase to even the amorphous, and then again another crystalline phase. And that we, you can see the selected area electron diffraction pattern also. So this is the pattern which is just ice grown sample. This is again the intermediate, I think this 350 degrees Celsius heated sample, which shows the amorphous phase. And when we again heat it at almost 650, so you can see at the 650 you are again restore the crystallinity, but in the different phase, and that is again visible here. So by this way we say that recrystallization happened. And then after we heat treated the same sample in another environment, that is the oxidizing and non-oxidizing. So we have taken different gases, and we heat treated in even presence of ammonia, which is a reducing environment, and even non-reducing environment, or like oxygen also. But again, we made the electrode, we tested the electrochemical performance. But as I said, these are the powder form, so they are not having a very good electrical conductivity. Also, the response is not so fast. So it's okay. The material is sensitive. The performance is stable, which is the one requirement. But directly, these material we cannot use for photoelectrochemical performance testing, or maybe you can say to think of for further investigations. So we again moved with our older strategy. Can we develop the nanostructure directly on the substrate? So this is the one of the work where we grown this zinc tin oxide nanostructure directly on the substrate. And what was the strategy? Basically, see what we can investigate. So we just adopted the 2 point. Okay. If we just change the seed layer, because when we start the growth of these structures, it cannot grow directly. So we need to develop some kind of seeding at the bottom. So we use FTO as a substrate, and then we just grown the zinc oxide as a seed layer. So we adopted two approach. One is just we prepared the solution of zinc oxide and deep coated the layer, and another is the electrochemical deposition of the zinc oxide. So in this whole study, we just keep focus investigating what is the effect of two different seeding approach on their structural performance as well their photoelectrochemical performance. So here you can see that how the seed look like. So seed layer direct, basically this electrodeposition is more uniform and dense as compared to the dip coated. And this is the structure. So if you look like they are not look very different, but though they have the differences, the electrodeposited had a different structure which is very tiny at the bottom, but the top surface is slightly look like circular form, where they have a thicker at the bottom and but not that much slide at the top, and structural is almost look like same, not very different things are there in those seed layers. Then this was the interesting figure when we investigated their absorption profile. That's a very different because their morphology is playing a very critical role. But when we tested the electrochemical performance, you can also see the current versus time profile plot when we just make chop light off on off profile. So it's a very clear cut differences between these two systems. So the electrodeposition system shows far better performance. Even the efficiency is also very high as compared to the these two systems. So what logic we have given that in electrodeposition system, since you seen that the seed is more compact and it is having more clean nature, so structures are also more dense on that systems, and the layer is also very thin at the bottom. Basically the, you can say, the bottom of these rods. So we are getting more active surface at the electrode. So even we also calculated the electrochemical surface area, and that was very high. Then we also investigated how the charge injection capacity, the performance, separation performance. In all these calculations, we found out that electrodeposited seed layer is shown much better performance. This is the another electrochemical investigations. So our just objective was to understand why and which layer is giving better performance in this setup. So I think these just some calculations, how we calculated and what was our logical explanation behind this. Another experiment, so within the same strategy, we just also willing to modify the morphology again. So we adopted another agent as a surfactant, which is helping us to control the growth of these structures. So process was similar as reported in the previous work. We just slightly added this surfactant during the reactions, and we achieve the differences in the morphology. As you can see here, this is the seed layer, this is the sample which is prepared without using surfactant. But when we use the PG and PVP as a surfactant, you can see the differences in their orientation, even the morphology, even the size. And that we again confirm the structural properties are look like similar, only the morphological changes are there. And these morphological changes is contributing again, and we could get almost performance. If you see here, the current is almost 1.5 milliamperes. So now you can ask the comparison what I have shown earlier. So in other metal oxide systems, the current was almost less than 1 milliampere, but in these systems we almost able to get 1.5 milliampere per centimeter, even higher, without having any kind of coating or surface modification yet. So we are still planning to modify these systems for further performance or the improvement. I think so. I can summarize here time. So I have just given the idea. We can use the low temperature solution based approach, and we can develop the nanostructures, and which can give us the large active surface area. The process is also whatever I have shown is very simple. In any lab you can do, in any chemistry lab it's possible. It's not very expensive setup is required. The electrode can be efficient if we can control the defect, because earlier whatever I have shown the studies. So our target was to just control the surface, look out their defect profile and how the defects profile is getting changed, and just correlate their performance. So we have observed that if we are tailoring the surface, we can effectively change. If let's say the change of 50%, that is very high. Okay, so that kind of change is there. And surface functionalization or the surface modification helping us to reduce the defect. It is also helping us to improve the stability and electrochemical performance. and also helping us to improve the light harvesting. But still, if you see that these are not the enough, we required further design and the creation on this material to improve the performance. So that is the message. If we are working on this domain, we need to look out this. So with this, thank you very much. I would like to thank my collaborator, also the funding agency, to support our research, our group members for working on this domain. And this is our campus. If you'd like to interact, so these are some of the picture, the back side. Actually, we have almost 20%, 30% forest reserve in the campus, and it's become very beautiful. We have several man-made water body in the campus. So thank you. If you have any query or maybe the question, yeah, nice.
Based on electrolytes. But in future, if we want hydrogen to be a major energy source, then in that case, the salts produced might become a problem for the environment because they're inorganic. So, is there a possibility of using adsorption type catalytic methods in your technology instead of using electrolytes because they might become a problem? Is there a possibility?
Okay.
Okay.
So
So,
see
see,
here
here
we are
we are
just
just
trying
trying
to
to
test the
test the
performance. So
performance. So,
therefore we
therefore,
are
we are
using the
using
electrolyte.
electrolyte.
But
But
see,
see,
we
we
need
need
to at
to at
least
least
move the
move the
ions.
ions.
So
So,
ionic
ionic
movement
movement
is
is
required in
required in
this
this
process.
process.
Therefore, we
Therefore,
need the electrolyte. But now people are targeting, can we use some kind of water, let's say the sea water, which is already having these kind of ionic things are there. But the another issue is that we require the simultaneously very pure water. So that challenges are there. So see, our target is to mainly develop the electrodes, but of course, those who are having the understanding of more chemical processing or the electrolysis of the electrode process, they can think of this problem, how we can cater the issue of electrolyte or maybe the more pure need of the water. So yeah, it's a really one another issue which we have to think of. That's why I said it's not only the one domain. There's a lot of components are involved there, and we have to look out where we can help or we can work, which is related to our understanding. Okay, thank you. Yeah, any other? Okay, if not there, maybe we can interact outside also if you feel hesitated. When I don't feel, if you feel need to discuss here in the open forum, you can ask any question. If not, then maybe we can talk outside. I think now I can hand over to chair. Maybe they can decide. Yeah, please. Thank you very much.
Thank you very much, sir. In Department of Applied Physics, there is all synthesis facilities available for the development of nanomaterials. Here, we are also preparing the nanomaterials subjected to optical applications. There is a slot of visit of research facilities in afternoon. Please visit. We have high temperature furnace up to 1500 degrees centigrade. These furnaces are programmable. We have hydraulic press. We have electro workstation. A lot of facilities are available. Those participants or scholars who have come from various places can come and take the results. Thank you very much, sir.
Thank you so much, Dr. Ajay Kushwaha, for a fruitful lecture. And in spite of many distractions, you still continued. So, thank you so much for that. Now, I would like to invite our session chair, Dr. P.K. Jhinge, to share his valuable thoughts.
I hope the topic covered by the Dr. Kushwaha from IIT Indore and the results shown through the slides and their teamwork. This shows that the lot of work is going on the new field, particularly for the fluid hydrogen, and what are the challenges that can be executed through the use of hydrogen in future. because of the environmental problems with the present fuel, right? So I hope that the presentation given by the Kushwaha sir is really helpful in the conference to the researchers for doing work with the fluid hydrogen. Thank you very much for your presentation.
Thank you, sir. Now, I would request our session chair, Dr. P.K. Jhinge, Dr. Kamal Kushwaha, convener of the conference, Dr. S.K. Mahobia, co-convener of the conference, and Dr. Vasudha Saxena to please felicitate our speaker guest, Dr. Ajay Kushwaha, with a shawl, shreefal, a memento, and a certificate. I would request all the participants to please join us for the high tea. There's a special announcement. All the registered participants can take their high tea coupons from the registration desk. Thank you.